Hello again, and here I will be discussing the number 2 of problem set 2. So in number 2, we are asked to find the equivalent resistance in terminals A and B, which is this terminal and this. It can be interchanged since resistances have no polarity and there are no sources found in the circuit. So we are going to find the equivalent resistance or the total resistance of the whole circuit. Again, you want to look at the circuit and what do you call this? You want to simplify it furthermore before you solve for the total resistance, so that it would be simpler to solve. So here I found that there is a delta formation right here, which I could later convert into or transform into a Y formation so that it would be simpler. So I redraw the circuit again to form a delta, then use this to, and then I would convert this delta to a Y formation. I'll be drawing my guide again. So for me to get the resistances of these resistors of the Y formation, I would be needing the resistances of the delta. So to get the resistance of this, I would multiply this adjacent resistor and this adjacent resistor together, then divide them by the total resistances of the delta formation. That would give me 180 over 31 ohms for this resistor. For this resistor, its adjacent is 20 and 12. So multiply that and then divide it by the total value of resistance for the delta, and I would get 120 over 31 ohms. Lastly, this resistor here has an adjacent resistances of 30 and 20. Then divide it again by the total resistances, you would get 300 over 31 ohms. As I'm done converting the delta to Y, I put the Y formation into and insert it. Replace the delta formation in the circuit. So here it is, but it still looks very complicated. So then again, you would want to simplify it or redraw the circuit to make it more easier to look at. So then I redraw the circuit. So here we could see that there are some elements that are the most inner in the circuit. So it is very optimizable to simplify it from the inside. So here, since this is the inside most part, you get it, we are going to sum up these two resistances since they are connected in a series. So that would give me 1980 over 31 ohms. Then again, I would rewrite it to a more simpler circuit. So there are still elements that are connected that are still complicated or inside the circuit. So I would get the total resistance of this parallel circuit. That would bring me to a formula for parallel resistances. 1 over the first resistor, which is 180 over 31 ohms, plus 1 over 1080 over 31 ohms, which is the second parallel resistor. That would give me a 165 over 31 ohms. So here it is. Here it is. It is even more simplified. So then this connection over here is connected in series, so might as well put them or add them up. So 300 over 31 plus the recent resistance that we have solved, which is 165 over 31 plus 10 ohms. It would give us a value of 25 ohms. And again, we have simplified the circuit. So we only have a 5 ohm resistor and a parallel resistor and a 15 ohm resistor. So again, we're going to make this a series circuit, so we could just add everything up. So again, we're going to find the equivalent of these two parallel resistances. So again, the formula for the parallel to find the total value of parallel resistances is this 1 over this resistance, first resistance, plus 1 over 25, which is also this resistance. So adding all that up, we got 35 over 2 ohms for this. So this would be the final phase of the circuit, which is only composed of a series circuit. So we have this 5 ohm resistor here, the 35 over 2 ohm resistor, and the 15 ohm resistor. So add them all up, we got the total total resistance, or the equivalent resistance for terminals A to B, which is 32.5 ohms.